everyone, in today's video we are going over how to use a random forest classifier from the scikit-learn Python library to do a multi-class classification task. But before we get into the code, let's go over some prerequisite knowledge, mainly what multi-class classification is and what the random forest classifier model is. Multi-class classification is a machine learning technique that divides data into more than two classes, and there's multiple ways that this can be done. The first is one versus the rest. In this approach, a binary classifier like an SVM or logistic regression is trained for each class that there is. For example, if you have three classes, circle, square, and triangle, three different binary classifiers are trained. So there would be a model for circle, a model for square, and a model for triangle. So there would be a model for circle that would treat an observation being a circle as a positive case and the other two classes as a negative case. The same would be done for the square and triangle classes, and the model that returns the highest probability would be the class that the observation is classified as. The second type of approach is one versus one. In this approach, a binary classifier is trained on each pair of classes. So in the previous example, a model would be trained for circle versus square, circle versus triangle, and square versus triangle. And the third method is using a model that is built to inherently handle multi-class classification tasks. And this includes models like Random Forest and XGBoost. Now that we know what multi-class classification is, let's briefly go over how the Random Forest classifier works. But to do that, let's first quickly review what a decision tree model is. Decision trees are a model that use a series of questions or statements to classify an observation. So for classifying something as a square, the decision tree might have several questions or statements such as, does the object have four sides? True or false? And if that is true, then it may ask, are all four sides the same length? True or false? If that is true, then it may ask, are all the sides connected at 90-degree angles? If that is true, are the sides connected so the object is closed? If that is true, then the observation is classified as a square. A random forest model is an ensemble model that trains multiple decision trees on the data. Each decision tree model is trained on a random subset of the data and the features. Then each of these decision trees classifies an observation into one of the classes, and the class that is predicted by the most decision trees is the one that the random forest classifies the observation as. So now that we have all our prerequisite knowledge, let's jump over to a Jupyter notebook and look at our data and define our multi-class classification problem. So today we're using a Spotify Tracks dataset. And first, let's just take all our necessary import statements. So here they are. We're really using pandas, numpy, matplotlib for some plotting, and the random forest classifier from scikit-learn. All right, so the first step is to read in our dataset, and we'll take a quick look at it. All right, so when we take a look at the first few rows of this data set, we see we have a track ID, the artist, the album name, the track name of each of the Spotify tracks, and then there's also these numeric columns that kind of show some metrics about the song. So you can see there's like a danceability score, an energy score, a loudness score, a speechiness score. This data set also has a track genre, and this is going to be our target variable in our multi-class classification task. We want to see if given these numeric features of a song, we can classify what genre the song is. Now, as a first step, let's just look to see how many unique values we have for track genre. So here you can see we have quite a few distinct values for track genre. And we can also print out the value counts for this. And here we can see that this is a pretty well-distributed data set. All the genres have 1,000 rows in them. Now we could build a classifier that classifies songs into any one of these categories, but for the interest of this video and the interest of time, I'm actually going to limit these genres to just one of 6 genres. So only include track genres that are pop, country, hip hop, punk rock, Latin, and EDM. Now next, let's drop the unnecessary columns from the dataset, the columns that we're not going to need in our model. These are things like the unnamed column, the track ID, and the non-numeric columns. So we can just use the pandas drop function for that. And we will specify all the columns that we want to drop. And we'll do axis equals 1 to specify columns, and we'll do in place equal to true. Now these are the ones we want to drop because either they don't provide us a lot of useful information for the model, or they're text features instead of numeric features. So unnamed 0 is not providing us any information. We don't need track ID in the model. And these are all non-numeric data columns, which Random Forest doesn't accept unless we encode them. However, there's so many unique values for this that encoding it will add some complexity that we don't want to get into for this video at least. And time signature also is not giving us too much valid information, so we'll drop that as well. And while we're doing this, we'll also check for any missing values and we'll drop those as well. Now, I believe that this data frame does not have that many missing columns, but we'll check. As you can see here, there's only one row that has an artist, album name, and track name missing. So what we'll go ahead and do for that is just drop that row out. Next, we want to define our features and our target variable. Features are the columns that are input into the model, and the target is the output that we're looking to get. And the features are normally stored in a column called X, and the target is stored in a variable called Y. So that's the naming convention that I'll use here as well. So we have X and Y, and we'll take our Spotify tracks dataset. And for X, we'll define that as all the rows and all the columns that are not equal to track genre. So that's going to give us all those numeric columns about the rows, like the danceability, acousticness, all of that, and it's not going to give us track genre. So this will be assigned to X, and then we'll do comma, and we want track genre as our output as our Y. Next, we're going to split our data set into a train, validation, and test set. The train set will be used to fit and train the model. The validation set will be used to track performance as the model is being trained and tuned. And the test set will be used at the very end as the last step to test how well our model works on data that was unseen during training. So we will use scikit-learn's train test split function, and we'll define xtrain, xtest, ytrain, and ytest. And here we use scikit-learn's train test split function, and we'll pass it x, and we'll pass it y, and then we'll pass a test size of 0.2. This means that 80% of the data set will be saved as xtrain and ytrain, and 20% of the data set will be saved as xtest and ytest. And we want to set the random state for this function. Random state just makes sure that every time you run this notebook, you get the same results. If you don't set random state, then when you run the notebook, each time you run it, you might get slightly different results. And the number you set this to doesn't really matter. I've seen a lot of people use 42, so I'm just used to setting random state equal to 42. But you can use whichever number you want, just make sure you keep it consistent throughout your notebook. Now, in some cases, you might just stop here and create a train and test set. But today we also want to create a validation set so that we can keep track of the performance of the model after it's been trained and after its hyperparameters have been tuned. So to do that, we'll actually just copy this again, and we're just going to create the validation set by splitting up this xtrain set into an xtrain and xvalidation set. So we'll just need to replace this with xtrain and ytrain. And we'll change this to 0.25 so that the validation set will also contain 20% of the original data set. So we'll change this xtest and ytest to xval and yval because these are now the validation sets. And again, we have random state equal to 42. Now I do want to emphasize that this test set, you're only going to see that be used once at the very end of this notebook. And that's because once you define your test set, you only want to use it once to evaluate the performance of your final model. So you don't want to predict anything with the test set until you have trained the model and you've tuned the hyperparameters and you've determined that the model that you have is the final model that you want. Then you use the test set, because the test set is only supposed to be used once. And once you use the test set, you can't use it again. So I really just wanted to emphasize that point. The next thing we need to do is we need to encode our target variable. Now remember, our target variable is the track genre, and that is a nominal categorical variable. And random forest can't deal with categorical data inherently, so we have to encode that. So to do that, we're going to use the label encoder function that's provided by scikit-learn. And what this will do is it will convert all those categories to numbers. So since we have 6 categories, it'll convert each one of them to a value between 0 and 5. So everything that's a pop genre song will be converted, that track genre will be converted to, let's say, 0. Everything that's a country song will be converted to 1, and so on. Now this step needs to be done after splitting the data set to avoid data leakage, and it needs to be done on the training, the validation, and the test sets for consistency. So once we have our label encoder, so we will fit transform this on the Y-train data set, and then we'll just transform it onto the Y-val and Y-test data sets as well. Just change this to val and change this to transform. And we'll do a similar thing for test. After encoding the target variable, we also want to apply a standard scalar function to the feature variables for xtrain, xval, and xtest. Doing this will make sure that all the features have a 0 mean and unit variance. And this isn't completely necessary for a random forest model, but it might help boost the model performance a little bit, so we'll apply that transformation to each of the data sets as well. So scikit-learn has a standard scalar function, so we'll use that, and we will fit it to the xtrain data set. And we want to use that exact same scalar to transform the validation and test sets. So for the validation and test sets, instead of doing fit transform, we'll just do transform. And again, this is a step that you need to do after splitting the data to avoid data leakage once again. So now we're ready to actually create the random forest model. So here we'll define our model as RF model. And the first thing we'll do is we'll actually just create a random forest classifier where we'll just set random state equal to 42 like we did earlier. And we won't give it any other hyperparameters. We just want to see how the default random forest classifier performs before we do any hyperparameter tuning. Now we'll just fit this model on xtrain and Y-train. And the next thing we want to do is we want to use our validation set to see how well this random forest model with all the default hyperparameters, how it performs on unseen data. So we'll take our RF model and we'll use the predict function, and to predict we will pass xval. This is our validation set. And we want to get the accuracy of these Y predictions to what the true Y value is for this xval data set. And the true Y values for the xval data set is the yval data set. So scikit-learn has a function called accuracy score. This will return the accuracy, which means how many times the model predicted the correct class. We will pass to that yval, which is the true Y values in the validation set, and ypred, which is the values that this RF model is predicting for the validation set. And we can print that out. And we can also print out a classification report, which will kind of show how this performed for each class. And then we can also print out a confusion matrix. This confusion matrix will show how many observations in each class were correctly predicted. And it will show you which ones were wrongly predicted and what they were actually predicted as. So let's go ahead and run this. All right, so our validation, this should actually be validation accuracy, is 0.6942. That means about 69% of the time this model is correctly predicting the right class. Here you can see in our classification report, we have each class broken out here and the precision, recall, and F1 scores for each class. Now down here is where you see the confusion matrix. So here you can see that 159 actual class zeros were classified correctly as a class 0. Now 0.69 is not a bad accuracy score, but we want to see if we can boost that a bit by tuning the hyperparameters of the model. Hyperparameters are parameters that the model doesn't learn from the data, but instead parameters that we as analysts or data scientists manually set. And different combinations of these hyperparameters can lead to better or worse results. So for random forest, we can define what's known as a parameter grid. So I've defined that here. And this lists out some of the hyperparameters that the random forest model takes. And then it lists out some values that we want to test out for those hyperparameters. So here I'll just quickly go through some of what these hyperparameters are for. So N estimators, this is the number of trees in the forest, and generally a higher number is generally better, but it does make the model slower. Max depth is the maximum level of each tree. A deeper tree can model the complexities in the training data, but it might not generalize well to unseen data. Max features is the maximum number of features or columns to take into account when making a split. And minimum leaf samples is the minimum number of samples required to be in a leaf node, which is a node that cannot be split further. After we define the parameter grid, we will define the model once again and make sure to set that random state to 42. Now, scikit-learn provides a GridSearchCV function, which takes the model and the parameter grid and it systematically tests each combination of parameters to determine which combination gives the best accuracy score. So we will define that here. It's GridSearchCV. We'll pass it the model and the parameter grid. Now, GridSearchCV looks for the best hyperparameters using cross-validation. Instead of using the entire dataset to train the model, it'll first split the model into a specified number of subsets or folds. And that's something we can define in this function. And we want to tell GridSearchCV to use 10 different folds. And what will happen here is that GridSearchCV will split the training dataset into 10 different subsets or folds. The model will be trained on 9 of the folds and then will be validated or evaluated on the remaining fold. This process will be repeated 10 times and each fold will serve as the validation set once. The final performance score for each hyperparameter combination is the average performance across all iterations. So we'll just finish out the arguments here. Like I mentioned earlier, scoring will be using accuracy. And you can pass this a different scoring function, but for right now, we'll just use accuracy. And the last two parameters this takes is njobs and verbose. This njobs just tells GridSearchCV to run more than one job when you set it to -1. Now we will fit GridSearch to our training data set. And we want to save out the model with the best hyperparameters, which is the one that gives the highest accuracy score. And we can do that using the best estimator attribute of the GridSearchCV object. And finally, we can print out what the best parameters are. And that will be stored in the best params attribute. And we can also print the best accuracy score, which is stored in the best score function or best score attribute. Now we'll go ahead and run this. Now you can see here it's fitting 10 folds for each of 360 candidates, totaling 3,600 fits. Now this GridSearchCV will take a while. In this case, it's going to take around 10 to 15 minutes for it to loop through each unique combination of all of these hyperparameters. If you have a lot of different values for each hyperparameter, or you just don't want to wait the 10 to 15 minutes, instead of GridSearchCV, you can use RandomizedSearchCV. And what that will do is it will pick random combinations of these hyperparameters to test out instead of testing out every single combination of hyperparameters. Okay, so this actually took slightly closer to 20 minutes, but these are the results. So here you can see that the best parameters are where bootstraps equal to true, max depth is none, max feature is square root, min samples leaf is 1, and n estimators is 300. And the best accuracy score we got was 0.72. Now that is slightly better than 0.69, so tuning the hyperparameters helped a little bit. And for the sake of this video, I am just going to leave the performance here, and we'll move on to testing the performance on the test set. But if you thought that this performance needs to be better, you could go and change these hyperparameter values or add more hyperparameters into the parameter grid and run GridSearchCV again to see if you get a higher accuracy score. So now, as our final step in this model creation, we will take the best estimator, which is stored in best RF. So this is the model that has all the hyperparameters set to these values, and we will use it to see what the performance is on our test set. And this is the one and only time we will be using the testing data set. So let's define the Y predictions again. We'll take that best RF model and we will predict what the genres are for the X test data set. And we can actually copy all of this code from up here because we're still using test accuracy and we still want the classification report and the confusion matrix. We'll copy it down here, and the only thing we need to change is instead of yval, we are now using ytest. So I'll run this, and we see on the test set, the accuracy is 0.70. Now that's a little bit worse than 0.722, but the performance on the test set is expected to be a little bit worse. Now if we were getting something like 0.5 or 0.4 or something really low, then it means our model is not performing as well as it should. But 0.7 is a pretty good accuracy score. And here also we can see the confusion matrix and the classification report for the test set as well. Now the very last thing I wanted to show is the feature importances that the random forest model returns. And feature importance tells us which features or which columns contributed the most to the model's decision-making process when it was classifying each observation. So we'll create a variable called feature importance, and we'll take that best estimator, best RF, that's the random forest that has the best hyperparameters. It has an attribute called feature importances. And we will set feature names equal to x.columns, so that we'll have the column names or the feature names that were the most important. And I have this code that I wrote before that will create a graph of the feature importances, so I'm just copying that down here. And here we can see which features were the most important for classifying Spotify tracks as a certain genre. So here we can see that popularity was considered the most important, but then things like danceability, acousticness, speechiness, those were the next most important in helping the model determine what genre a Spotify track is supposed to be. And here we can see whether or not the song was explicit, what mode it was in, its instrumentalness. Those ones were less important. All right, so that is how you would use the scikit-learn Python library to train a random forest classifier for a multi-class classification problem. In next week's video, I'm actually going to walk through the same example, but using an XGBoost model instead. So if you're interested in that, make sure to subscribe so that you know when that video goes live. I really hope this video was helpful for you. If you have any questions over any of the code I used or over random forest or multi-class classification, let me know in the comments. Thank you so much for watching this video, and I hope to see you in the next one.